Hello. So this is the second lecture. So in the first lecture, I started to explain some circuit variables. So I started with Q. Yeah. And then I give you the relation between Q and I. So actually, as you see here, if Q is given in the question, you need to differentiate it to get I. Okay. And you know from calculus, if I is the differentiation of Q, this is the same thing if, or this is equivalent to Q is the integration of I. Okay. So actually we have this formula. We have also this formula here. This one is used if you have Q and you want to get I. This one is used if I is given and you want to get Q. So then after that, I give you several examples. I explain to them. I told you Q is a function of time. I is a function of time. Yeah, I give you several examples here. After that, I started to explain energy. So what do you mean by energy? So to understand energy, we need to start with work. So what work means? And here in this course, we are talking about electrical energy. You know, we have different types of energy, but it looks, I think this definition is universal. But anyway, so let's see the definition here for work. So if you have an object and you apply a force F to the object, and because of this force, you were able to displace the or to move the object by L. So in this case, we can say the work is actually F times L. Okay, that's what I explained last time. So, and then energy is actually energy that a quantity that represents the ability to do work. So energy or work should be the same thing. Okay, energy can describe your or the ability to do work. So even they have the same unit. So the unit here, F is Newton, as you know, L is meter. So Newton times meter is actually joule. Okay, and this is the unit of the work or the energy. Okay, is joule. After that here, also I told you, for example, if you have a battery this way and you have a lamp here, for sure if you open the switch, so there is no current, it's gonna pass and the lamp should be off. But if you connect the switch, what happens is the charge or the current, the charges start to move from A here, is gonna go all the way here and then go to this terminal here and then repeat again. So it should be continuous current. And this current, actually, what happens now is we are transferring energy. We are transferring energy from the battery to the lamp. Okay, that's why the energy consumed by the battery should equal to the energy. Sorry, the energy generated by the battery should equal to the energy consumed by the lamp. Okay, and actually, what we did here, this energy actually is the result of chemical reaction. So there is some chemical reactions that can make electrical energy. And actually, we converted this electrical energy into light and heat as well here. Yeah? Usually when we generate electrical energy, we can use in batteries, we use chemical reactions, or you can we in generator, if you use generator, so here we convert the mechanical energy into electrical energy. Okay, this is a very popular two ways to generate energy. Okay. Um, Now I'm gonna define voltage. Voltage. So if you have here, if you have here a battery this way, as just I have just explained. So if you have a charge dq, okay, coulomb, this is a unit of coulomb. This is not power, this is a coulomb unit. So if you have dq, q is a charge, okay, and this dq consumes dw. W is the work or energy when moving from point A to B. Okay, so here we assume in order to if you have dq charges are moving from A to B, they consume dw energy. In this case, we define the voltage as follows. So the voltage is the amount of energy consumed, which is dW divided by dQ. Okay. In other words, to make it very simple, this is one way to define voltage. It's actually the amount of energy consumed, okay, to transfer dQ charges. dQ charges. That means if the higher the voltage here, you can have higher energy, more energy to generate or consumed from the battery. So now let's so this is, we call it, look, this is the symbol we are using, VAB. This means this is the voltage between point A and point B. Okay, that's how we define it. Voltage usually it's like potential difference. You got what I'm saying? So usually it's between 2 points. Voltage between A and B, between point A and point B. Okay. Now let's look at the unit. Maybe you already have some background and you know voltage. We use volt. Okay. I think this is very popular. We use it in our daily life, volt. So actually, based on the definition here, voltage is energy divided by Q, right? So energy is joule. It's in joule. A Q is a charge. It's in coulomb. So actually the unit is joule divided by coulomb, which is a volt. So the volt means joule divided by coulomb. Okay. One more thing here, when I say VAB, as I told you, VAB means the voltage difference between A and B. Okay. So this one, I can say this one is equal to VA minus VB. Okay. So if I have here AB, so VA minus VB. So the difference between the volt at A minus the volt at B. But the question is, what do you mean volt at A with the volt of A or volt of B? Because as I told you, usually voltage means difference between 2 points. Okay. So when I say A and B, VA, what this means? Okay. So it means this is the difference between A and a common point or reference point. Okay. Usually we call it ground. Okay. So let me just make it simple here. So I'm gonna show you something or explain something here in the. Okay. So for example, if you have a battery this way, okay, and then you have resistance here, another resistance here, whatever. Okay. So I have a voltage difference here. Okay. So for example, if you want to call it AB, okay, so we have VAB. This one B and this one is C. So I can say the voltage difference here is VBC. Okay. And this one here from here to here, because this is all of this just 1 point. So it should be VAC. Okay. This is point A and this is point C, as I'm going to explain. So you can see here always voltage is voltage difference, VAB. But now I'm just telling you VAB is actually VA minus VB. So what it means when you say VA or VB, it means this is the difference between point A and a common point or a reference point. Usually, for example, we can take this point node and consider this one like ground. So when I say VA means the voltage difference between A and the ground or this common point. Same thing when I say VB. Okay, so it's a difference between VB and the ground. Okay, so that's what you should understand when I say VAB. Okay, it means the difference between A and B. That's why it's VA, the difference between point A and point B. Okay, and this one should equal VA minus VB. VA is actually the voltage difference between A and the ground or the common point here. I select. Okay. Same thing for B. So hopefully you understand. See, you're not confused here when I say the voltage of a point. Okay, so actually it's not voltage of a point. It's a point to the ground or to the common point, but just we say VE. Okay. So anyway, so here mathematically you can see here if we say VBA, look, the order is very important. VBA. So here VAB, this is BA. So VBA is actually VB minus VA, okay, which is actually negative VAB. Negative VAB. Okay. So you can switch, but here you will see there is a negative here. So VBA is actually negative VAB. Okay. Let me also make some clarification here, because you will see now this sign may make some confusion, but let me make some clarification. For example, if we have a resistance this way, okay, and then I tell you this is A and B. If I tell you VAB, okay, is equal to 5, okay, 5 volt. Okay? That means A is above B by 5 volt. Okay. But here, if I say VBA equal negative 5, okay, that means B is below A, okay, by 5 volt. So it's almost the same thing, but this sign can tell you which one is bigger than the other. Okay, so if VAB means VA greater than VB, okay, but VBA, okay, so that means VB is less than VA, or VA is greater than VB. Okay, so sometimes maybe this sign confuse you a little bit, but what I'm saying is that I can say the voltage here from here to here, it's positive 5. That means this voltage in B is greater than this voltage by 5, okay? But if I take the voltage this way, it should be negative 5, okay? That means this one is smaller than this one by 5. So this is, I hope you are not confused here in the sign. Also, you are not confused about when I say, what is the difference between when I say VAB? So that means this is the voltage difference between 2 points, okay? So here we have point A and B. Also, when I say VA only or VB only, VA also voltage difference, but between A and the ground, a common point. This one between this one and this one. Okay? Maybe I tell you something here. Usually current flows from high voltage to low voltage. Okay, it's similar. Maybe you can see voltage. It's like position. So, for example, water usually moves from high places to small to low places. Okay, so it's gonna flow this way. So you can see the high place here is like high voltage, and this one is a small voltage. It's almost the same idea. So current flow from high voltage to low voltage. Is that okay? Okay. So now you should understand the voltage difference, VAB. You should understand when I say VA alone, point A or point B. Okay. A or B, these are point here, this point and this point. Okay. So here, and VBA is equal to minus VAB. Okay. Yeah, so here this is similar to what I said. When a charge moves from A to B, actually what happens here, you transfer the electrical energy from the battery to the load or to the lamp here, and then the charge is gonna come here, and because of chemical reaction here, the charge again is gonna gain energy, is gonna also come again here. So that's what there is a flow, continuous flow of charges here. Now I'm gonna move to the next point, which is the power. This power actually, it's very important, and you will see power and energy are too close to each other. I'm gonna tell you what is the difference. So power and energy delivered to an element are very important. For example, when you buy, I can tell you something very simple. When you buy a light bulb, and this light bulb is 300 watt, and someone buy 100 watt, okay? So the 300 watt should give you more light than the 100 watt. Is that right? That's what we know, right? Simply because this one here is going to consume this amount of power, 300 watt, because it's going to consume more power, we're going to get more light. Okay, because power is not wasted. If you take some power, you just convert the power from one form to another. Okay, so this one is consuming more electrical power, which means it has to give me more light and more heat. Okay, so anyway, so what is the relation between energy and between power? Okay, so energy is just the rate of change of power is the rate of change of energy. So if there is a time included here, so this should be power. Okay, so power consumed or generated. Okay, so battery generate power. Is a bulb here is actually consuming power. Okay, so actually here the power means, it means how much the power here, it means how much amount of energy, okay, per second. So here the time component is involved here, the power energy per second. Okay, for sure higher energy consumed here so it should be more light, more heat. Okay, because this energy we're not you are not going to waste energy. Okay, you just convert it from one form to another. Anyway, so that's why if you look at the unit of the power, it's actually joule, which W is energy or work. The unit of W is joule. Okay, divided by time. Joule divided by time, that's what we call watt. Okay, so watt is actually joule divided by time. Okay, if you have any question, you can. I know this is. Uh, I mean for this one to be more recorded lecture, and I really appreciate that some students had time to attend. But if you have any question, you can interrupt me. No problem at all. Okay. So now you can see here, power is the rate of change of energy. Okay, and we explained before, voltage VEB is actually dW divided by dQ. Okay, that's what I explained before. Also, we explained I energy, I current is dQ by dt. Okay, dQ by dt. Okay, so now what I'm going to do right now, I'm going to get a very interesting, very important formula for the power. So let's start with this one here. Power is equal dW by dt. Okay, from calculus, I can do something like that. I can put here dQ and dQ. Okay, so here this one is equal to this one from calculus. Okay, it's so as long as this one is equal to this one, I can do that. Okay, but why you did that? Why you put here dq and dq here? Okay, so I just added. So this one is equal to this one. I just put here dq and dq. Okay, so why I did that? Simply because I want to get a relation between dw dq, which is v, which is the voltage. dq by dt, it's actually I. So by this way, but by this very small manipulation of this equation, we can find that the power is actually V times I. Is that okay? V times I. This power either generated or consumed. So let me make it simple. So for example, here V and I. So as you will see here, for example, if I have a battery, the battery generates or is gonna generate power or supply power. Okay, so for example, I have two resistors this way. So this one generate power, this one consumes some power, this one consumes some power. Okay, so the power consumed here is V, the voltage here, times the I, the current going through it. Same thing here. The power consumed here is V, the voltage difference here, times I. Okay, the power generated here is actually V times I. I is moving this way, times I. Is that okay? So for any element, either resistance or battery or whatever, the power generated or consumed. So here it's consumed, but here it's generated. Okay, so the power generated or consumed should be I times V, the voltage across the element times I going through the element. Okay, as you also will see by in this lecture, again we don't waste power or we don't lose power. What happens is that what happens is the amount of power generated here should equal to the amount of power consumed here plus the amount of power consumed here. You got what I'm saying? So as you will see, for example, if I generate here 10 watt, so the total power consumed here plus the total power consumed here should equal to 10 watt. So if this one is 2, so this one should be 8. Okay? So because the power is not going to go anywhere, right? So we generate certain amount of power. So every one of them is going to consume this power. So as you will see now. So now the important formula we are going to use now is power is equal V times I. Okay, and I was able to derive it this way. Okay. Yeah, so also we can do something here related to, yeah, for example, here you know from calculus, P is dW by dt. Okay, so I can say W is the integration of P dt. That's what I did here. Okay. And B is actually V times I. So this another way you can calculate energy this way. So energy, the amount of energy is actually the integration of VI times V dt. Okay. Okay. So next year I want to tell you some elements we call it active elements. Usually, and some elements are actually passive elements. Okay. So active elements here, these are the elements that generate power, like battery. Okay. But some elements are consuming power. We call it passive. Okay. So let me tell you, go back here to what I explained here. So, for example, if you have a battery this way, this is a positive side, this is a negative side. If you have resistance this way, this is a positive side, this is a negative side. If you have another resistance here, this is the positive side and negative side, okay, or voltage, okay. So first of all, what do you mean by positive and negative? What this means here, okay? It means the voltage here is greater than the voltage here. Voltage here is greater, okay? Voltage here is greater than this one. Same thing, voltage here is greater than this one, okay? So negative here, it's not necessarily means it's a negative voltage. It doesn't mean that, okay? That means this voltage here is higher than this one, okay? Maybe both of them are positive, but here sign polarity positive or negative means the voltage here is greater than this one, and thus the current has to flow this way. Here also the current has to flow this way. Anyway, so what I want to tell you here, because these two resistors are passive elements, you can see in case of passive elements, the current flows from positive to negative, as we see here. Okay, so for passive elements, it flows from positive to negative this way. However, if you look here, if you look at the battery, which is active, the current has to flow this way. So the current is flowing from negative to positive. Okay, so in case of battery, or in case of active elements, the current will go this way from negative to positive. But for resistors, it's from positive, or for passive elements, from positive to negative. That's what I'm explaining here. Okay, so let me see what I'm explaining. So here I'm explaining active and passive. Okay, polarity, how we make the polarity. So for example, that's what I have just told you for active convention. So here, for example, you can see this one like a battery. Okay, so the current has to come get out from the positive side, as I told you, or it has to the current has to get into the device from the negative side. So if this is the case, this is active. Okay, so here the current leaves the device from the positive terminal. Okay, the current enter from the negative terminal. This is active. But if I go to passive is the other way, the opposite. So okay, where current has to enter from the positive and has to leave from the negative. Either this way, it doesn't matter if you put here positive or positive here or negative. It doesn't matter, because in both cases the current enters from positive here and get out from the negative. Okay. Now, when you calculate P equal VI, so for this device, after you calculate B is equal to VI, this should be the amount of power delivered or generated or supplied by the device. Because if it is active device, it has to generate power. Okay. Here, it should be B is equal VI, and this is the amount of power consumed or received or absorbed, whatever you want to call it. Okay, anyway. However, listen to me. However, because maybe this part a little bit confusing, but hopefully I can clarify it very well. Look here, guys. Hopefully you understand this part very well. So look what I'm saying. If I have a resistance this way, okay, connected somehow, and then I tell you the current I is equal to 4 ampere. Is that okay? I. So I can simply assume the current is moving this way. I can do that, but in this time I'm going to say negative 4 ampere. You got what I'm saying? So what I want to see here for the current, what it means if current is positive or negative. Okay, so this is very important. Current, same thing with voltage, it has a value or magnitude. Here in this case is 4, and the sign here is going to tell you about the direction. Okay. So in the future, as you see in this course, if I give you a circuit and you solve the circuit, after you solve the circuit, first in the beginning, you don't know how the current will go. So you can assume, you can make any assumption. I can assume this way, okay, which is totally fine. And then after I calculate, it. If I find, for example, this one is 2 ampere, okay, that means the direction I selected is correct direction. If I do the calculation and I found this one negative 2 ampere, so what it means? It means that it's a correct direction should be the other way. Okay. So hopefully this positive or negative does not bother you as long as you don't get correctly. Okay. So here, if the current flowing this way is 4, so I can say the other way here is negative 4, because positive or negative, it means the direction. Okay. So it's negative this direction, okay, which that means if you make it positive, so in reality it has to be this way. Okay. Same thing for voltage, by the way. For example, here, if this one is positive and negative, and I tell you this is 5 volt, okay, so I can say simply this one is negative and this one is positive, but this time I'm going to make it negative 5 volt. Okay. So here, this positive or negative is related to the direction, which one is positive, which one is negative. As by the end of this chapter, I'm going to give you example. You will see in this example, I can assume any polarity, okay, because after you do the calculation, it will correct itself. How it's going to correct itself, as I told you. If I assume the current this way and then I calculate it, I find it's negative. That means it has to be the other way. Okay. So, but anyway. So here, what I'm saying here is, okay, sorry. Yeah. So here, what I'm saying, if you calculate the power, okay, and you found the power is positive in this case. So in the very beginning, I assumed the device is active. If that's true and this device is active and the direction of the current, everything is okay, so the power you have to calculate should be positive. However, if you calculate the power and you find it is negative, okay, what it means? It means this element is not active. It consumes energy or receive energy, okay, and this negative, it comes from the direction, so it should be the other direction. Okay, so the current should not be this way, it has to be the other way. And if the current enter from the positive, that means it is passive, okay, not active. So what we can do, I can assume it's active, I can assume this way, and then I do the calculation. If I find the power is positive, so my assumption is true, it's active, and actually this device delivers or generates or supplies power. Okay. If I after do calculation I find it is negative, so that means this device actually is passive and it's actually consuming power. Okay. Same thing here. If I start with the assumption it is passive means the current enter this way, okay, and then I do the calculation. If I find it is positive, that means the directions are correct, okay. But if I find it is negative, that means it has to be the current should get out. So I assumed it's passive, but it's actually active. That means it generates or supplies power, okay. Here, this is a example. I think this is the last example in this chapter. This is a very small chapter. So here in this one, it's related to what I have just explained right now. It's related to 2 points here. You should understand, number one, the amount of power generated should equal to the amount of power consumed in the circuit, okay? Because this is actually the conservation law. So this is related to physics, the law of conservation of energy. Okay? So the amount of power generated should equal to the amount of power consumed. Okay. This number one. So you understand better here. Number two, also what you can understand here in this example is how can you calculate power? You calculate power by every element V times I. Multiply V by I. Okay. Voltage by I. And this power can be consumed or it can be generated. Okay. More importantly, also, you will learn in this example is about the direction. Because I know it's maybe a little bit confusing. The direction is it positive, negative, whatever. Okay, so let's start with this one. So I give you this circuit here. I'm telling you we have element 1, we have element 2, we have element 3. Whatever these elements are, so they can be batteries, can be resistor, whatever. Okay, so without details, we have element 1, element 2, element 3, and then I give you, this is given to you, the current has to go through this way, 2 ampere. So 2 ampere, it has to come this way. Okay, so current has to be this way and 2 ampere. And also I give you, this one is positive and this one is negative. So this voltage is higher than this voltage, and this one actually 6 volt. Okay, this one here, this one is negative, this one is positive, and this one actually 4 volt. This is given. Okay, so now I want to calculate the power for each element, the amount of power generated for each element. Okay, so the first we have to do is I need to define. We need to assume voltage, the polarity of the voltages. For example, this one. Number one, you need to assume the polarity of the voltages and also the direction of the current. Okay, and after that you can do the calculations. Okay, as I told you, look here, the current here is coming this way. I know it's coming this way, but it's not wrong if I assume it's this way. Okay, this is arbitrary, so you can assume the current anyway. It doesn't matter. Okay, why it doesn't matter? Because you will find it's after you do the calculation, you find it is it's negative, so that you can correct it. So that's why here I'm asking you here. I'm going to assume it in a certain way, but when you solve it, you can try to assume the power and the current and the voltage in a different ways, and then all of them should give us the same results. Okay? So for example, here I'm going to assume for element number 3 here, the polarity is not shown here, but I'm going to assume this is positive and negative. Can I assume the other way? Yes, you can. It doesn't matter. You can assume the other way. Also, I assume the current is going to go this way. Okay. Here, for some reason, I want to assume the current coming this way. Okay, you can assume the other way, but here I assume it's coming this way. Okay. Yeah, when you solve it, you can assume it's coming this way. You can do that. And then here it's this is given to me. This is positive and this is negative, so I can keep it. This is positive and this is negative. Okay. Here the current is already giving me the current is moving this way, so I can keep I1 this way. Okay, or you can make it the other direction. It doesn't matter. Okay, but I'm going to tell you what matters now. What matters now is, because this one giving me 2 ampere. So this current is this I1 should be 2 ampere, positive 2 ampere, because it's the same direction here. But when I calculate I2 here, it has to be negative 2A, because it's given to me the current is moving this way. You got what I'm saying? It's moving this way. So this one should be negative 2 ampere. But anyway, you will see right now. But again, all this direction, just your choice. So you can, if you want to make it this way, that's okay. Okay. For some reason, also just I want to show you, if you do the problem correctly, the direction you are selecting doesn't matter, because it will correct itself. Okay, as you will see right now. So here, although it is given to me, this is negative and this is positive, so I'm going to switch it. I'm going to make this one positive and this one negative. But wait a second, why? So when this one is positive and this one is negative, actually this one was 4 volt. If I flip them, so this one has to be negative 4 volt. You got what I'm saying? Negative 4 volt. Again, If you are not comfortable to do this way, okay, you can keep this one positive, negative. You can keep this one negative, positive. Okay, you can make the current direction this way. You can make the current direction this way. Okay. And this one you can select assuming the current is going to go this way, so you can assume the current as I did here, and you can assume this one bigger, this one, or the opposite. It does not matter, okay, as long as you did correctly. What do you mean by you did correctly? I mean this current is giving me 2 ampere this way, so anything that's moving this way is going to be 2 ampere. Anything that's other way should be negative 2 ampere. Okay? It's given to me this, if this is positive, this is negative, 6 ampere. So if you want to switch it, this is negative, this is positive, so this one should become negative 6. Okay, this is what I mean. So let's start with okay, I decided to select the direction this way. That's why I asked you here, try to do a different way, try to do it in different direction, and to try to see if you will get the same results or not. Okay, so let's start with element number 1. Let's work on element number 1. So element number 1, you can see here the current is entering from positive to negative. So here I'm assuming it is passive. I'm assuming this one passive because the current is moving from positive to negative. After that, I'm going to calculate the power. If the power is positive, so my assumption is correct. This one is passive. Passive means it is receive power. Okay, but if it is negative, that means my assumption was wrong, and it has to be generate power. So this one should be generate power. Anyway, so let's do it. So what happens here, as you see, power is V times I. So V is the voltage here times the current. Okay, this current, let's start with I1. What's I1? It's 2, positive 2 ampere, because it's in the same direction like this one that's given to me. So the current is positive 2 ampere. Okay, what about the voltage? I told you it's this one given to me. This one positive, this one negative, this one is 4 volt. So this one should be negative 4 volt because I switched it. Okay, I assume this is positive and this is negative, so it should be negative 4 volt. Okay, so after that, simply I'm going to calculate the power of this one. I don't know if this power is consumed or you will see that. Now, based on what I did here, I'm assuming this power is consumed. Why? Because the current is moving from positive to negative. Okay, so anyway, so but let's see. So after I do the calculation, I found it is negative 8. So because it is negative 8, so actually this one is not passive element. This should be active element, and then it has to generate 8 watt. Okay, and it has to generate it has to generate. So this one it's actually generating 8 watt. Okay. And actually, this makes sense because actually, you know why? I'm going to tell you why. Because it's given to me the current is this way. Okay, so I use the same current. Okay, however, I assumed I flipped the polarity. It's given to me this is negative, this is positive. You got what I'm saying? So if you repeat the same question and you take this one here, you don't change what I change it here. This one is active. It's very obvious this one is active because the current here is entering the negative part. Okay, is if a negative terminal. If it is entering negative terminal, so it is actually active. Okay, I assumed it is passive, but the calculation corrected it. Okay, because I got it negative. Okay. Let's see the other one. Oh, I'm sure also we have something wrong here. I'm sure. You know why? I'm going to tell you why. This one positive given to me. This is positive and this negative. Okay. Here positive, negative. That's okay. But here it's giving me the current has to be this way. But I flipped it. Okay. So anyway, so by this one, I'm assuming this one is active because the current is entering from the negative. I'm assuming it's active. Is that okay? And let's see if I get positive at the end, so my assumption is true. If it is not, so actually it is not active, it's passive, and it has to absorb. Again, it's very obvious here because it's based on what's given to me here, the current is moving from positive to negative. Anyway, so in this case, the voltage here, this is a big one, positive, negative 6. Okay, so actually the voltage is 6. However, I assume the current is this way, and actually the current given to me this way. This way is 2 ampere. So this way is negative 2 ampere. Okay, so that's what I did, negative 2 ampere. So to calculate the power here in this element, so you just multiply them, and this one should be negative 12 watt. Okay, and again, because this one is I in the very beginning I assumed it's active. Okay, because current is entering this way, but actually it turned out to be passive. So this one is actually generate power, but this one is actually consuming power. Okay. Let's see the last element, number 3 here. Okay. Number 3 here. The only here I don't know, the polarity is not given to me, so I'm gonna assume this is positive and this negative. The current here is this way. Is that okay? The current is this way. This current is easy. So again, in order to calculate the power, you need to get I and you get V. Okay. I here is equal to I here, and it's in the same direction. So I should be 2 ampere. That's the easy part. I here is 2 ampere. This is the easy part. Okay. Now I want to get the voltage here. How I can get the voltage here? Okay. Look, how can we do it? So that means I want to get the voltage between point A and point C. A and C. So voltage A and C. Okay. I don't have this one, but I have this one and I have this one. So I can use the information I have here in order to calculate this one. Okay, I'm going to tell you how. So VAC. So I know VAB. AB I know it. BC I know it. So I have to put B. Okay, so what happened here, VAC is actually VA minus BC, as I told you before. So what I'm going to do here, because I want to represent VAC in terms of AB and BC. Okay, so I should have B. So here I'm going to add B and subtract B. I didn't do anything, right? So here I add B and subtract B. And then I'm going to take this one, VA minus VB is actually VAB. Okay, VB minus VC, okay, is actually it's VBC. Okay, so now I can calculate VAC, the voltage from A to C, which is this one here, in terms of VAB and also VBC. VAB, we got it before, right? Which is 6. This one is 6 given to me, right? It's VAB. Okay, it's the same direction. It's a positive, it's negative 6. It's not negative 6. It's, if I tell you VBC, it's negative 6. But VAB, it's positive 6 because it's the same direction. So this one is 6. Now let's look at this one. I want to get VBC. Okay, VBC. So VBC, because this is a negative and this is a positive, okay? So this, so actually, so here, so this one has smaller voltage than this one. So V from B to C, is actually negative 4. You understand? That's what I explained here when I told you. If I have a resistance this way, and this is from here to here, it's 4 volt AB. So from here to here, actually it can be negative 4, okay? Or this point is higher than this one by 4, and this point is smaller than this one by 4. Okay, this is the meaning of it. But anyway, so let's go to the example we have here. So here we have, so the voltage here, VPC, okay, from B to C, okay? So this one should be actually negative 4, okay? Negative 4, because it's positive and this negative, okay? And already VBC, we already got it here, here, okay? V1 here, okay? Anyway, so after that, okay, so now I got the voltage VEC. So I got the voltage here VEC, okay? When you calculate the power, you have from the positive to the negative, VEB, VEC times I3. So now I'm gonna multiply it. And now I'm assuming this one is active in the very beginning. I assume it's active because the current enter from the negative part, okay? And then I got the power positive. Okay, because the power positive, so my assumption is true, and this one is active, so it's generating power. Okay, so summary, let's say summary for element, for this element, we found this element generate for what? This element here. This element here, element number 2, is absorbing, is consuming 12 watts. This element here, number 1, is actually generating 8 watts. So we have 2 elements, okay? One is generating 8, the other one is generating 4, and we have one consuming 12. Okay, so that's what I told you. So the total amount of power generated is actually 8 plus 4, and the total amount of power consumed is actually 12. They have to be equal. Otherwise, if they are not equal, something is wrong in the calculation. That's for sure, because this is the conservation of energy. Okay. So the total energy generated is 12, consumed also 12. Any questions? Okay, again, this is just a very small chapter. In this chapter, we just made some definition about power, about current, about voltage, and these things. So we're going to use them all the time. Okay. Now I'm going to start the second chapter. You may be scared that in the first week we finished one chapter recap, because it's just a very small chapter, so it's not too much anyway. So in the second chapter here, it's about the circuit elements. As I told you in chapter number 1, it is any circuit is actually circuit elements connected together. We connect them together. This is the definition of any electrical circuit. So in this chapter, I'm going to talk about some circuit elements like resistors, some sources, energy sources, and I'm going to say here independent voltage source. We have voltage source, we have current source, and for each one of them we have dependent and we have independent. So we need also I'm going to talk about switches, voltmeter, ammeter, and so on. So these are some elements of so some elements here. Example for elements is actually a lamp, battery, heater. By the way, the lamp is represented by resistance. Okay, is modeled by resistor. Heater is the same thing. I model it like resistor. Okay. So here, what I'm telling you, if you have an element or device, okay, this device has a voltage V, this is a positive, this is a negative, and current enters this way, okay. What I want to tell you here, there is a relation between voltage and current for the element. And this relation is different for different component. Is that okay? Maybe later in this course you'll understand better, but for now, if you have any element, this element should have voltage on this element, and it has current. And the relation between them, it depends on the component itself. Okay. Sometimes this relation is linear. Okay. In case of linear devices, sometimes it is non-linear. Okay. So there is some relation, and this relation. So today we are gonna focus on resistors or resistance. So we're gonna assume this relation is linear. Anyway, so the second thing here we are talking about is actually energy sources. You can tell from the English name, energy sources, okay, electrical energy sources. So this is our active element. So this element actually is producing power, okay. So when you produce power, we are gonna classify it into two sources. One is voltage source, the other one is current source, okay. Again, both of them are producing power, okay. But what is the difference between them? Why is this one we call it voltage? Why is this one we call it current? Okay, simply because in case of voltage, the voltage across the source is fixed. It does not depend on the rest of the circuit. However, the current may vary, may be different. Okay, so let me clarify it here, because this is very simple. It's not difficult. There is no need to complicate it. So look here what I'm saying. So what I'm telling you, energy sources, we have two types. One is called voltage. Okay. In case of voltage, for example, you have a battery here. Okay. Battery is this one. So why this is a voltage source? It's a source of energy, but we call it voltage. Why it's voltage? I'm going to tell you why. Because the voltage here constant, ثابت. So the voltage here is 9 volt. It's constant. Based on the rest of the circuit here, maybe I'm going to get 1 ampere. It may be in 2 ampere, 3 ampere. So the current may change depending on the circuit, but the voltage is fixed. It's the same. Okay. And be careful here. When I say fixed, I don't mean it's constant. I don't mean that. In this case, for sure, it's constant. But in other cases, for example, maybe the voltage here, for example, is A sine omega t or 5 sine omega t. So it may be sine. So the current here, so the voltage here, is a sign. Okay, it's time dependent. Okay, it depends on the time. So, but still, all the time, this is the voltage. All the time, this is the voltage. But maybe I'm gonna get different current here based on the rest of the circuit. Okay, so hopefully you understand what I mean here. So what I'm saying here in voltage sources, the volt, either if it is constant, like in case of battery, or if it is sine, still I'm gonna get the same. Yeah, this one it changes with time, but I'm gonna get the same signal all the time. Okay, but the current will be different. It depends on the rest of the circuit. Okay, so the smaller the resistance I put here, the higher the current. Okay, so the current can be different. This is for voltage sources. Now, what about current sources? Again, you can tell from the name current sources. So current sources here, it's the opposite. So here the current always constant. It can be 5 ampere, it can be fixed 5 ampere, or it can be 5 sine omega t. So sine, but it does not change. Okay, what it changes here with changing the circuit, what is the voltage here? It change based on the circuit. Okay, so again, very simple. So we have two types of energy sources. One is called voltage source, the other one is called current source. Okay, in voltage source, the voltage does not depend on the rest of the circuit. Okay, but the current does. Okay, um, for the current source, the current is fixed. It does not depend on the rest of the circuit, but the voltage does. You got what I'm saying? The voltage can change, but the current is fixed. So this one is providing fixed color. Okay, fixed current. Okay. Anyway, so now, so as you see here, voltage source. Hopefully you understand. So voltage source, it can be if it is constant voltage source, we can make it this way. Battery. So it's going to be like fixed, constant. It means constant over time. So if this one 5 volt is going to be always 5 volt, but this one function in the time, it can be sine, can be anything, but it changes with the time. Okay. So this is constant voltage source. So always the voltage here is constant. When you change the circuit, you change the current. The current out of this one, it changes. Okay, based on the circuit. Here, what happened here is that this is a symbol for voltage source. This is how it looks like: circle, and then you put positive and negative. Okay, this voltage is always the same value. Okay, but the current here changes. It changes based on the circuit. For current source, the symbol is different. As you see here, we make an arrow this way. So this arrow is telling me the current has to go this way. Current, and this current is constant. Okay. Again, constant doesn't mean it's constant in value, but it doesn't change. It can be function, whatever sign, it can be sign, but by connecting whatever you connect here, it will be the same, but the voltage may change. So for example, the bigger the resistance I put here, the bigger the voltage. The smaller the resistance, the smaller the voltage. Okay. Since that's what I'm explaining here. Okay? Any questions here? So this is another important component of. Okay, now, so now we have for energy sources, we have two types. We have voltage and we have current. Okay, now I'm gonna make another classification. Okay, so some of them either voltage or current. Some of them we call them independent. Other ones we call them dependent. Okay, so dependent on what and independent on what? I'm gonna tell you. So independent means, okay, so the voltage here does not depend in any the source here. The voltage is fixed, and independent current source also the current is. So here it means the amount of voltage here or amount of current here is does not depend on any other elements in the circuit. Okay, so let me clarify it, because maybe I don't want to be confused here, but let me make it simple, because we agreed if this is a voltage, voltage source. Okay, so that means the voltage here should be fixed, either for example 5 volt constant, or it can be sine, but it should be fixed this way. And by changing the circuit here, the current can change. It can be different current. Okay, that's what I said. So if the value of this voltage that's constant, if this value does not depend on any other elements in the network, or it's at constant all the time, for example 3 sine omega t, so this one we call it independent. Okay, however, this one, the amount of the voltage here, okay, it can be dependent. It can depend on another element in the network, okay, or sorry, in the circuit. So if this is, for example, you have here resistance, whatever. So here the value of this voltage is actually depending on this one, but still the current will be different. Okay, so the only difference is, just I'm gonna clarify it now, is here, in case you can tell from the English name, independent. It does not depend on anything. The voltage here is fixed. The voltage here is fixed. The current here is fixed. However, dependent sources, the amount of the voltage here, it depends on other elements. Okay, other elements. So how can you know if this is simple? Simple here we use a diamond. So you can see a diamond here, and then here I put positive or negative. Okay, so this one, as you see, positive or negative. So that means this is a voltage source. This is also voltage source. If I use an arrow this way, so this one current source and current source. Is that okay? So now I'm gonna make another classification. Now look here. Okay, so this is a voltage. This is a voltage source. That's okay. However, the value of the voltage here, it depends on another element in the circuit. We call it V0. Is that okay? So the value of this voltage here, okay, which as I told you, it's fixed unless you change this element. So if you don't change this element here, so this one is fixed and the current it changes. Okay, so this one is called voltage controlled because the voltage here depends on in V0. V0 is a voltage of other element in the circuit. Okay, it can be, as you see here, the value of the voltage here is actually depends on a current. So there is a current that can control this voltage here. Okay, there is another voltage. That's why this one is called current controlled voltage source. Voltage control voltage source. So this is a voltage source, voltage, as long as you see a diamond, positive, negative, this is a voltage source. Okay. However, if the value of the voltage here depends on another voltage in the circuit, that's what we call voltage control. So we can control this value by changing this voltage. Okay. Here, this one is controlled by the current. Okay. Same thing here. As long as you see a diamond, so it is any diamond. If you see a diamond, so this is dependent sources. And you can tell from the English name dependent because it depends on the value depends on other elements. Okay, so for example here, this one current source, but this one voltage control, this one current to control, because to control the value of I, okay, or I is controlled by a voltage. Okay? Here I is controlled by a current in the circuit. Okay, so I'm gonna give you more details here. So, for example, I think, yeah, so let's, because maybe a little bit confused. Look here, guys. For example, as long as this one is diamond this way, so this is dependent source, okay? And positive and negative, so this is a voltage source and dependent, okay? Now, what is the value? What is the value of the voltage here? It is 5I, and the I is actually the current coming here. So here, the value of the voltage, this one is independent because always the voltage is 24. Okay? It does not depend on any elements. It's always 24. But this one actually here depends on the current here. Okay. By changing this current, this one it changes. Okay. If this current does not change, this one fix it. It's not going to change. Okay. So, but based on the resistor in the circuit, the current can change for sure. Same thing here. Once you see a diamond here and once you see arrow this way, so this one actually is a current source. When the current is moving this way, okay, and the value of the current here is 0.2 V. and V is actually the voltage here. Okay. Anyway, so this is actually this dependent sources. Okay, tell me, maybe this is a little bit confusing, because if the battery I have, the battery we are using in daily our daily lives, any battery you are using, this is independent, right? The power you get from the wall is also independent. So tell me what scenario where I have a battery that depends on other things. In reality, this will be used to model amplifiers, model transistor, and so on. So in if you are using an amplifier, the output voltage, okay, is actually proportional to the input voltage. For example, the output voltage, for example, is 100 times the input voltage, because you amplify the voltage. So I can see the output here, or I can model the output as a voltage controlled voltage source. Okay, so for example here, this is a transistor. For sure we're not going to teach transistor here, but I just want to give you some idea about it. How a source, a voltage source, can have different current value or voltage value. Okay, so as you see here, for example, this is a transistor. If I want to put it in a circuit, we model it. So I model it this way. Okay, you have current IB, which is the current here. You have a resistor here. This is the value of the resistor. This is E, which is equivalent to this one. And then I'm gonna model the operation of this transistor. I'm gonna put here a current source, because this is how it behaves. This current, it's providing you a constant current. Okay, and this current actually, it's actually GM, which is a constant, times the VBE, the voltage here, VBE. Okay, so this one is telling me this transistor is behaving like a current source, and the value of the current moving this way is actually depends on the voltage here, VBA. Okay, so if you don't change VBA, so this value is constant. Okay, if you change VBA, so this value it changes. Okay, but still it's just a current. It's current. The current here is equal to this value. The voltage may change based on the circuit, the rest of the circuit, and so on. Any questions? What's the time now? Still have 10 minutes. Okay, so I think I have explained this part about active convention. It's just a review. Okay, I told you in case of if you assume the device is active, or if you are using active convention, so the current has to get out of the positive. If you assume it is passive, so the current has to enter from the positive. Okay, and here's the power generated, here's the power consumed. Okay, I think I explained this one in the previous chapter. Okay. So here, example for active elements like battery generator, because they generate power. Examples of passive elements that consume power: resistor, lamp, heater, and so on. The other thing here I want to teach what we call electrical node. So what node means? Okay, I'm going to tell you what node means. So if you have a circuit, something like that, okay, you have source here, source to source, and you have some elements here, okay. So actually, the word node means a connection. So all this connection, I can call it only one node, okay. I can call it one node. So I can say this one is A, all this connection, okay. This point here, this connection here, I call it B. This connection here, all of this is just one point, okay. One point. The voltage here is equal to the voltage here. So that's why, because all the point here has the same voltage, so it has to be the same node. Okay. So all this connection here is the same node. Just I want you to be familiar with the word node. Same thing here. This connection here, all this connection here and here is just one point. So voltage here is similar to the voltage here, similar to voltage here, similar to voltage. Same thing here. Okay. One thing here, I think I have already explained it before, is So number one, what you should understand here, if you have, as I told you, electrical circuit means we have electrical elements that's connected together. You connect it together using wire or using metal or using copper. Usually we use copper to connect them together. Okay. So number two, you need to know what I mean by node. Node. Okay. So node means the connection. Okay, that has the same voltage. So here's the voltage here. All of this has the same voltage. So this is one node. This is another node. This is another node, another node, another node here. Okay. Don't tell me this is a node and this is a different node. No, it's not different because all of them have the same voltage. So it's gonna be the same. It's just 1 point. You understand what I'm saying? So this node is the same like this one, this one. That's why all of this should be only one node. Okay. Same thing here. This one is the same like this one, this one. All of this is just one node. Okay. Anyway. So these are the nodes we have here in this circuit. As I told you before, usually what we do, we take one node and I consider it like this, the common or the reference point. Okay, as I told you before. So, and this is actually your choice. You can select anyone. So it doesn't matter. So actually what happens here when I say, as I told you before, when I say VA, the voltage of A. So actually I mean here the voltage, the difference between A and the ground. Okay. So actually, again, let me say it again. We have different nodes. We take one node and I consider this one is a common node. So any voltage here, I'm going to say, when I say VA, so it's actually between A and the ground. Okay. VB, it means between B and the ground and so on. We assume this common point is the voltage of it is zero. Okay. We still have VAB. Don't be confused. We still have VAB. Okay, because any voltage has to be difference between two, VAB, VBC. Okay, but when I say only VA, what do you mean? I mean VA means it's between A and the ground. Okay, so here VA means VAN, VB means VBN. Okay, and if I subtract these two, okay, I'm gonna get VAB. I think we can. Okay, we can work on this example. It's not difficult one. So here, this example is very similar to the example I explained before about the power. Okay, we want to calculate the power. We want to prove that the power absorbed should equal to the power generated. Okay, so here this is given to me. I want to calculate the power of each element. Okay, so so here let's start, for example, with element number one. Okay, so element number one, you can see the current is coming this way here. And it's 4 ampere coming this way, 4 ampere. So you can see this one is coming from entering from the positive to the negative. Okay, so this one is passive one, because this one is coming from the positive to the negative. Okay, so here the power is equal V which is 12 times I, which is 4. Okay, so 48, and this power absorbed because this one is passive. Okay, so here in this element we have 48 watt consumed. Okay, let's see the other elements here. Let's look at this one here. Okay, this one here, the current is 2. It's given to me, and even all direction are given to me, so I don't have any problem here, or I don't need to assume anything. All direction given to me. Okay, so the current is coming from here. It's 2, and it's entering from the positive to the negative. Okay, so as long as it is from positive to negative, so this is passive. Okay, so I'm gonna multiply 2 times 24, which is 48 consumed. Okay, so here we have 48 consumed here, we have 48 consumed here as well. Let's look at number 3. Okay, in number 3 here you can see the current is moving this way. It's 2 ampere, is moving this way from positive to negative. So this one is actually also consumed. Sorry, this one is passive. Okay, I'm gonna multiply them together, 56. Okay, so you can see here in this circuit we have 2 sources. These 2 sources are generating energy, 2 sources here. And we have three elements that are consuming energy. See, this one consumed 48. Let me go back. This one consumed 48, number 1, 48, and this one 56. This is the total consumption we have. Now I'm gonna see how much power these 2 generated. For sure, as I said before, the summation of these 2 should equal to the power consumed. Power generated equal to the power consumed. So now let's, for example, let's look at this one here. Okay, this one here we have 4. This 4 ampere is going to move this way and come here. So this one also 4 ampere. Okay, so you are going to multiply 4 times 36. So this one 144. Okay, and you can see the current here is entering from the negative. Okay, so this one actually is active or generated. So this one is going to generate 144. Okay, same thing if you look at this one here. Okay, this one, the current is coming this way. Okay, as long as there is no branch, so the same current here is gonna come this way. So this one is 2, so this one is 2, and you can see the current is entering from here. Okay, so here this one, because this one is dependent, and this one is 1 times ix, which is this current. So this one actually 4 ampere. So I'm going to multiply 4 ampere by 2 ampere. Okay, the total is 8. So in conclusion, that's very simple. That's similar to what I explained before. This maybe example is easier because you don't need even to assume any direction. I give you all direction. You just multiply V times I, and then you can see the total amount of power generated, which is this one and this one, this one and this one, 144 plus 8. It should equal to the total power consumed here and here and here. Okay? So summation of generated equals summation of received. Okay, so just I added 144 here plus 8 here should equal to this one, which is 48, 56 should equal. Okay, so this one, so make sense. The amount of power generated should equal to the amount of power consumed. Okay, I think that's enough for today. Okay, thanks very much.